So we briefly talked about drug depots, I believe, right? Okay. Basically, when you take a drug, it can bind other places than where it's going to do its action, right? Lots of times you'll stick those in muscle, fat, or those plasma proteins there in your blood. Not a big deal. Cool thing is, they don't do anything when they're hanging out there, right? It's not at an active site. They're not going to be metabolized. They're not going to be causing any sort of effect. But that binding is reversible, so what will happen later is you'll release that, that drug as you go and really have that available for later. So this is a great sort of way to build up. We'll talk a little bit about steady state and so forth later. It doesn't really affect the magnitude. Well, I mean, it does affect the magnitude in some sense, but once you take a certain amount of drug, you're going to reach a plateau, right? It's not going to give you like, wow, I've got this extra drug stored up in my bones, watch out. I'm going to get a boost from that later, right? It's not going to get you above the plateau, right?
Right.
But definitely duration is what's going to be important here, right? Because it deals with the concentration of the drug that's available to you, and it's really going to delay the effect of that drug, right? So anything that comes in, if it goes to an active site, that's awesome, that's going to do something. If it goes to a depot, then it's not going to do anything. So let's say you take, we're just going to make up a number, 100 of whatever, who cares. You take 100 of a drug, and 70% of that goes into a depot. Well, only 30% of that drug is actually doing anything for you. The other 70% is hanging out, and it's going to come out later, right? Now, folks have different amounts of depot binding. That's not surprising. This is really why some folks are one of the many reasons why some folks are more sensitive to drugs than others, right? So watch out for the depot binding. It's non-selective. Basically, it means drugs can compete for the same binding sites. It's not a big deal. The problem is, this can really cause you some real tricks, right? So occasionally that displaced drug, that concentration can jack up, right? So if you have some other drug coming in there, it's going to displace that drug, right? That second drug is going to bind, take up those sites. Where's that first drug go? Remember, set that 70% that we took, right? Floods right back into your system, right? And that's available for you to use, or I guess overuse, right? Is the real concern there, okay? This is one of many reasons why taking multiple drugs is not always a good idea, right? It definitely cause you some unpredictable effects, right? Well, I mean, they would be predictable to us, John, but not other people, right? Folks who are taking the drug. We would be sitting there because we know this. We would go, well, yeah, I mean, obviously if you take that second drug, it's going to screw around with the first one. You should know that, but again, only 17 of you registered for this course. So I can only expect 17 of you to know that now, right? But please spread the word. So this is kind of one that might be important to you folks, right? THC in your urine, okay? This is one of the reasons why you can use marijuana today, and some days later you can take a urine test and still test positive for that. Okay. Now I know none of you are doing anything that's illegal, right? So we're not worried about that. But let's say you live, and this is an area where you could have some actual legal problems, right? So, and I don't mean problems with the legal use of marijuana is what I should say, right? Let me phrase that properly. If you lived in, let's say, a state where the use of medical marijuana was legal, and then you worked in a state where marijuana use was completely illegal, you could still test positive even though you weren't under the influence of that drug if you were using it for some medicinal purpose, right? And that could cause you some serious problems.
Isn't Ohio getting ready to pass that?
And that's a real concern. Well, I mean, I guess this is psychopharmacology. I can tell you whatever I want, right? Mm-hmm. It's my class. Mm-hmm. This is one of the big problems, and Johnny, you probably know this as JP, you weren't in my addiction studies class, were you?
No.
Addiction studies. Kayla knows. So when we had the folks come in from the state legislature, right, and we had Delegate Lovejoy, who's one of the delegates for this area, right? It kind of depends on where you live. I don't know if you're in his district or not. You can think whatever you want about him, but he did come to my class, so I'll give him a check mark for that. I live in a different state now, so he doesn't get my vote anymore, but that's a different story. He came in and he was talking about the medical marijuana legislation in West Virginia, right? Which I don't know, I've not lived in West Virginia as long as some of you, but I am originally from this area, right? So I kind of grew up just 30 minutes from here, over in Kentucky. So when they said, hey, West Virginia is going to approve medical marijuana, I said, hey, it's time to wake up. I think you're still dreaming about something, right? Because I don't think anybody would have really predicted that was going to happen, right? But the problem with the legislation is it's a lot of problems. So one, you can't grow your own marijuana, so you have to actually go buy something, right? Which is really problematic for folks that don't have a lot of money. I don't know if you've looked at sort of the poverty statistics for the state of West Virginia. We don't have a lot of people, because we don't even have 2 million people, but a high percentage of those people don't have a lot of money, right? And so that's a real problem. So yeah, you still have to go out and you have to buy these expensive, extracts and oils and whatnots. The second sort of problem is, if you're going to start your own business, like, hey, how many of you thought, like, I'm going to start a dispensary, right? That's it. Seems like a reasonable idea, right, Brandon? I mean, it really does, right? Because you're talking some money. The problem is, are you a lawyer? No, but you probably want a lawyer to help you start a business. Those guys can lose their license if they help you, right? And that's a real problem, because then you've got all these people who might start small businesses, who might actually be bringing in some revenue to a state that, again, needs some revenue, because, oh man, I mean, we're making a fortune off that coal. Right? So, that's working out for us. No. As soon as somebody figures out how to make a time machine and they can bury more leaves to turn into more coal, we'll be okay. But up until then, revenues are dwindling, right? And so let's be realistic. So tourism is kind of a big thing. It's like our, in fact, I think that's the biggest industry in West Virginia is tourism, which should tell you something. Because I don't hear a lot of folks like, man, I'm going to take my vacation in West Virginia. But there are parts of the state that are very beautiful. So maybe we could have some people come, but you're not going to get any help. Because what lawyer's going to put his license on the line? I mean, he's got to feed his family, so you're kind of sunk there. So there's some real problems. I think the good thing about it is those folks who live in Ohio and work in West Virginia, or vice versa, because we live in an area where people, regularly, I mean, I drive through 3 states to get here to work every day, right? And when you're in that situation, I would say some of you, if you don't live in another state or work in another state, you know someone who does, right? It's not that atypical for here, but having that, legislation for those folks, I think is kind of the silver lining of that cloud. Because that could be a problem. If you were in Ohio, lived in Ohio, you were over there in Proctorville, using your medical marijuana, you come over here to work at the university and they drug test you. You're like, well, I've got a prescription. I was using it as I was, told to use it. I mean, I wasn't using it while I was driving the golf cart up and down campus. So, everything's fine, but there can be some problems. So there you go. I don't know, that's kind of a side story, but I think it was important. Works with this class, right? Makes sense. Yeah, that would have been a real moneymaker, right? Yeah. Well, what are you going to do? Other things, what else do we need to know about? I'm not going to hit you too much on these like first order kinetics, as exciting as those are, right? We'll talk in some generic way about how drugs are metabolized. I think you can really sort of get carried away with like zero order kinetics and which is cool. And there's some interesting like alcohol sort of applications to that, but I think for the most part, if you want to think about this, we really want to think about half-lives, right? I think that's a pretty standard, easy to digest sort of concept. You take a drug, and after some period of time, half of that drug has been metabolized. After some other period of time, another half has been metabolized, right? You continue to sort of step down by half every time, right? It's that's kind of the process there. So different drugs have different half-lives, right? And that's going to be important for the duration of that drug action, right? If you're going to give someone a drug that you want to be longer lasting, this will be particularly important when we talk about like antidepressants, for example, right? Nobody wants to take an antidepressant every hour, right? That seems a little invasive, right? But if it had a short half-life, what if it had a half-life of 30 minutes? Well, you might have to take it every couple hours, right? But if you have a half-life of a longer period of time, maybe 8 to 12 hours or something, you don't have to take it as often. And you can get to that steady state, concentration that you need to with sort of once a day or twice a day dosage, right? And that's why you'll take drugs, you'll see some drugs you take are once a day, some are twice a day, right? It sort of depends, again, it's on this half-life business. So there you go. A good thing to keep in mind is if that half-life is about 8 hours, you can take that drug once a day and you'll be fine. If it's a longer half-life, the problem is you really run into these problems with accumulation, right? And some folks, we can talk about this, some folks don't break down drugs as well as others. Some folks break down drugs better than others, right? A lot of this depends on your liver enzymes. There's a whole family of liver enzymes we'll chat about one of these days. Probably like this week or next. And those are the ones that break down most of the drugs that you take, right? Most everything you take is going to have some sort of business in the liver. They will do, you can do, these assays. You can look at folks, DNA and determine whether or not, they're sort of fast or slow metabolizers. And that's a real concern, right? And so that's really something. Unfortunately, they don't regularly test for that, and so they're kind of like, well, here you go, take this and see what happens. And then if you're one of these people in sort of an odd spot, then you end up with some trouble. So there you go. My wife is someone who has she has much more profound effects when she takes medication than anticipated. Yeah, no, it's bad. It's bad. She takes Dayquil and is out for half a day. It's like, that shouldn't happen. I'm
Doesn't
over
that
there.
have like an absurd amount of caffeine in it?
It
Like
does.
along with the medication?
She just like falls asleep. She's like, I'm getting drowsy. I'm over there like just drinking a bottle of NyQuil. Like, it's like, I don't feel anything yet. Let's just see how much more I need.
I tried that Z-Quil once.
Yeah.
It's nothing.
No, I don't.
No. Don't waste your money.
I'm not going to.
It was awful.
So there you go. Hey, here's some common drugs, right? And their half-life. Cocaine. I love when they put the trade or the street name on there, right? I don't know why. I just. I know, right? I mean, I think those up there because I think some of them are funny. I mean, you don't often get a laugh about cocaine, but when you can, I think you should.
It's the only one that has multiple names.
It is, right? I mean, and
I'm wondering if this exact conversation was held in the textbook room, and they were like, "We're going to do this."
Yeah, I don't know.
Somebody's going to get it.
But then I think maybe there was like, because I could see me doing this, like if I was on this, I would just be like throwing out crazy names to see what they would put on there, just to see if I could get Snow published as a, I'm just like making up names,
I'm like, who doesn't know that
It's cocaine.
cocaine?
Right, I mean, I don't know,
Yeah.
I don't know that it needs
Like
the
the other ones kind of make, some of
It
them
does
make
make sense, right?
but then,
I mean-
that one, like,
Yeah.
yeah, like.
Yeah, I mean, not everybody, I mean, morphine's just morphine, right? But whatever. But here are the half-lives for those drugs, so you can kind of see. So if you think about Advil, it's got a half-life of 3 to 4 hours. How often do you take Advil? Like every 8 to 12 hours, right? Okay, because it's got that shorter half-life, you need to keep taking that to still get that effect. You take your Aleve, you take that about once a day, right?
Mm-hmm.
And they recommend you don't really take a lot of Aleve, right? Because again, Aleve's got some other problems with your stomach, but it's got a half-life of 12 hours. So that's a little bit longer than that 8-hour half-life that we were really looking for that once a day. Now, let's look at this guy down here, fluoxetine or Prozac. Half-life of 7 to 9 days. right? That's a long time. This is why when you take an SSRI, it takes so long for it to be effective. So it takes you so long to build up to that right concentration. They don't want to hit you because it takes so long to break down. You know, they're not going to slam you with a big load of Prozac all at once, right? You got to take a little bit and you got to build up over time. And this is antidepressants in particular have long half-lives, and that really is important for prescribing and taking those drugs, but it creates that gap, right? From the time that you start taking the drug until you start feeling that relief, right? So a lot of folks will come in and they're depressed, and you go, okay, come back and see me in 4 weeks, like, you know, if you can make it that long. And you're going to be taking this drug, and you're like, well, this drug's not doing any good. That's not going to make you feel good. So I think it's really important to know ahead of time, like, hey, if you take an antidepressant, you're not going to see any relief out of that for a month. So just hang in there. If you and your medical professional have decided it's what you need, hang in there. It's going to get better, but it's going to take a month. What else do we need? We do need to get to that concentration, that constant level, steady state. Again, half-life is going to play a role in that. You want to get to the point where your first two steps there, right, that absorption and distribution is going to be equal to the metabolism and excretion, right? And so you want to be getting those drugs in and distributing those at the same rate that you're getting drugs out, right? So you're going to keep replacing, and as you replace, you're going to stay right at that sort of constant concentration level, right? So if you think about the university, right? I mean, the university's kind of like that, right? We're not really growing our student body. It's kind of been steady for a while. We've got as many students graduating and dropping out as we have new students coming in, right? I mean, both of those things happen, right? Okay, so let's just be realistic. Unfortunately, you know, not everybody makes it to graduation. We're working on that. It's getting better. You know, when we get to the point where we're hanging on to students better, we're not having students drop out, or we're recruiting more students, what we'll see is we'll see a growth, right? So that concentration would go up. All right, there you go. There's just a nice graphic. This is each time you take, you know, that drug over time. Notice you're kind of each time just building a little bit and rising up until you get to that desired steady state. Now again, you know, this could, if it's a drug with a short half-life, this could be a very short period of time. If this is a you know, Prozac, Zoloft, this could be weeks. So it all just depends on the half-life of that drug. That really makes an important it's an important factor to consider. There's one sort of example where the half-life thing doesn't really apply, right? And that's particularly drugs where you get the high level of the drug and the metabolism and elimination is sort of saturated, right? So you've sort of maxed out that process. Alcohol is a pretty good example of that. I don't know if anybody knows someone, I know none of you have done this, someone who's ingested more alcohol than they should have, right? Again, I know personally none of you have done that, right? Because you guys make better choices than that. But alcohol is a good example. You get that concentration level up so high, you've sort of saturated, right? You're not doing that half step anymore. You know, you're kind of moving at a steady state until you get down to where those mechanisms are saturated.
Is that why breathalyzers work? Because it's processed at a constant rate, so you can quantify it?
Yeah, I mean, you could quantify it even if it was a half-life situation, right? But it's going to be, the time changes are going to, it's going to be more linear rather than logarithmic up until you get to that first order kinetic business when the concentration gets lower. Here's a fancy word for you, biotransformation. Just means drug metabolism. We're going to take a drug, we're going to chop it up into things that are not the same drug you took. Typically, if we're working to get rid of that drug, the things that you've broken it down into are going to be less effective or not effective. And they're going to be they're going to be less lipid soluble. So you're going to be able to cram those in your kidneys, shoot those right out your urethra. That's going to be fun. And other times, you often take a drug that is not the effective drug, and sometimes you have what's called an active metabolite, right? So you'll take a drug, and then its metabolite is actually the effective drug that you want it to take, right? And so we call these prodrugs, right? So you take a drug, we're going to lop something off of that in that metabolism phase, and then whatever we're left with is actually going to do the effect, and then we'll break that down on a second step, okay? It just adds a step to the breakdown, but it's basically the same process, right? Nothing really new there. Let's see, what else do we need to know? Oh, you should know about these, what we call CYP450 enzymes. These are the guys, it's cytochrome P450. These are the enzyme family that really just breaks down most every psychoactive substance you're going to take. Okay, there are some exceptions. There are a ton of fancy things here that we might want to talk about at some point. You guys get excited about that. That's great when you do your presentations if you want to talk about the specific enzyme that breaks down the drug and things that can happen. This is particularly important with opioids. There's some, there's some interesting genetic variations in how folks break down opioids that have some important effects on behavior and so forth. But for right now, just know we've got this big enzyme family, the CYP450. That's what's going to be responsible for breaking down psychoactive drugs, which is mostly what we're going to talk about here. If you've got something that's screwing up the DNA that makes these enzymes, guess what? You're screwing up the process that's going to break down those drugs, right? Okay. So if they're overactive, if they're underactive, then that's going to happen. But if they're overactive, you're going to break down the drug faster. You think, well, I'll just take more of the drug. May or may not be a good choice, right? Sometimes it is, and sometimes it's not. If it breaks down more slowly, then you think, well, take less of the drug. That doesn't always work either. So there are things to consider, right? Unfortunately, again, your doctor's probably not going to bring you in and say, hey, let's see what those liver enzymes are going to do when we give you this drug, and we'll know how much to give you. And often they won't even look at your weight and say, well, they won't even do that. They'll go like, well, you're over 12, take 2. You're over 12 and you're also an offensive lineman for the Pittsburgh Steelers, just take 2. It's going to work. Who cares if you're 364 pounds,
Or 75 pounds.
Or 75 pounds, right?
Doesn't matter.
It doesn't matter. It's going to be the same. You're fine. Just work. They don't even take into account muscle content. There are a million things you should really look at when you're taking a drug, and they look at one of them, and that's the label. Right? And that's what's on there. Megan, that is not my. Please don't take my comments as a complete derision of, the medical professionals.
I was feeling a bit discouraged, actually.
Yeah, I'm working on it because I hate to see people go to medical school. I do. There are much better things you can do with your life.
I didn't do it.
You didn't do it, I know, and that's the only thing I like about you.
Oh, come on! Had a rough weekend.
Well,
I shouldn't expect anything else from you.
you should. But the reason I discourage people from medical school, Megan, is twofold. One, I think if you're an intelligent person, and I'm just going to assume everybody is until you prove me wrong, which may happen in 3 weeks, but I'm going to assume that for now. You often think, I have 2 options with my life. I can be a lawyer or I can be a doctor, right? There are lots of other cool things you can do with your life. Hollywood stuntman is wide open, but there are a lot of other things like graduate school, and research programs. And so I like to let people know that's out there, and you should think about those things. And then you're just going to go to medical school anyway. So it's a waste of my time, but I do it. I occasionally convince someone they shouldn't go to med school. You're going to get bored.
Bored?
Yeah, it's just, here's a cup, pee in it. I think that's what they do, right?
At the ears and you got it.
Oh, the ears.
Yeah.
You got to look in the ears, and you got to thump people on the stomach. I don't know what that does. Maybe I just have a weird doctor. But every time I go see my doctor, he's like, does this hurt? I'm like, yeah, if you keep hitting me, it's going to hurt. What do you expect? Well, what are you listening for? Is it like a cantaloupe? You're trying to
Make sure you spell right.
I don't know. But the doctor I see actually, he was Doctor of the Year like 2 years ago, right? So he got like some Doctor of the Year award. So I guess he's good. I only see my doctor like once a year too, because I'm relatively healthy and relatively young, so I don't have to go that often. What can affect that metabolic rate? A few things. What we call enzyme induction or enzyme inhibition. Basically, this means, are you making more of the enzyme or are we inhibiting that enzyme somehow, right? So if you, let's say you continually use a particular drug, or Bethany, even a class of drugs that are similar, okay? You'll often start making more of the enzyme that breaks down that drug, right? You guys have all heard of tolerance. We'll talk about tolerance. This is one of the mechanisms of tolerance, is this enzyme induction, right? So like alcohol dehydrogenase breaks down alcohol, right? Guess what happens if you continually drink alcohol? You'll start making more alcohol dehydrogenase, right? This makes sense. Enzyme inhibition, this is a fun one. This is when you'll inhibit those enzymes. This happens a lot. People always think about old folks, and I don't know why. I'm assuming young people eat grapefruits as well. But if you eat grapefruit, no, Megan's not a grapefruit fan.
Grapefruit's so good.
I know, I've got like 5 in my refrigerator, right? It's like I buy them all the time. There is a list of drugs somewhere like this long that are influenced by grapefruit. Grapefruit can actually screw around with some of the enzymes that break down those drugs, and it can cause some interesting problems. So you have to be aware of that. If you do eat a lot of grapefruits and you're on a medication, you should probably check. There's a website you can go to, and you can check and see if there's an interaction.
So I think even one of the birth controls
Yeah.
is on there.
I'm on 2 medications and I eat grapefruit.
You should check and see if those are on the list. Just make a personal note about that, because you want to make sure we don't need to know why you're taking those medications. They could be allergy medications or because you have a toe fungus. It doesn't matter.
Yeah, it's a toe.
It's the toe fungus. That's what I thought. But you want those to work. But I don't want you to give up grapefruits. They're a great healthy snack or breakfast. And if you can eat those, please do so. Drug competition. So again, if you're taking other drugs, they can sometimes fight for those binding sites. And then there are a ton of individual, I know this is like a really vague thing, individual differences. Age, gender, that should actually be sex. Right? But it's not gender. Again, people should read these things. And genetics, right? So, that makes a big difference as well. If you're older, you don't tend to break things down as well, right? So all of you guys just look forward to getting old. Things are not going to work as well as they do now. So get all the use you can out of the parts you have while you're young, right?
Yeah.
Because when you get older, those parts aren't good. Whatever part that is, whether it's your hands or your ears or your knees, whatever it is, use them now while you can. This is why I park as far away as I can at the grocery store, because I know in some decades from now I'm going to be on a rascal and I'm going to need to park close, but I don't need to now. I'm going to park far away. So age is big. Sex, we can continue this alcohol dehydrogenase story. Males tend to make more alcohol dehydrogenase than females. Sometimes, muscle content makes a difference in how you break down drugs and those depots and things. And then, of course, we've already talked about genetics. All right, enzyme induction, we talked about that. Inhibition, drug competition, genetic polymorphisms, we talked about that as well. Where are we? Slide 77.
Okay.
I don't know.
97. You were kind of close.
97.
You got one number right.
And here's another one of those enzymes. Again, we're not going to think too much about that. This is just a detailed story of people who are fast or slow metabolizers. Who loves urine? Everybody should, right? Should love at least getting rid of urine. Urine's a pretty fascinating thing, I guess. Some people get excited about urine. Kidneys are going to filter stuff. You're going to throw out whatever whatever drugs you have, that are in there. Sometimes we do need to monitor your drugs, make sure that your plasma levels are where they need to be. There are a ton of drugs where you need to actually have your blood taken on a regular basis, right? It's not atypical, they're just kind of measuring that. Some drugs don't need that. The problem is a lot of drugs have narrow therapeutic index, right? And so what we mean by that is, what's the difference between the dose that will make you feel better and the dose that will kill you, okay? And sometimes that's a lot closer than you want it to be. Something like Advil, oh geez, I mean the therapeutic index on that's like almost infinity, right? The only way you can die from Advil is if you choke on the pills, right? like that's how you die from an Advil overdose, is you swallowed so many pills, your esophagus got jammed up, and some of that went down the wrong pipe, and you stopped breathing, right? So otherwise, it's pretty wide. Now the therapeutic index for morphine, on the other hand, is pretty slim, right? The difference between, oh man, my broken leg doesn't feel bad anymore, and wait a minute, I can't breathe, is a pretty narrow window, right? And so you have to be careful about that. Advil, don't worry. Take two.
Just take two.
Just take two. I like when you go to the doctor and they're like, well, I mean, you can take 4 if you want. They'll tell you that sometimes, right? I really, the worst pain I ever had, I injured my trapezius, right? And if you don't know where your trapezius is, it starts at the top of your head and it goes all the way down to your foot. That's how bad it was. And it goes all the way out to my fingers. It was the worst pain ever. It is a huge muscle, right? It does start up in your neck.
It does.
And it goes out your arm just a little bit, like your shoulder, and it goes down your back. And they were like, oh, well, you can take 6 Advil, that'd be fine. I said, thanks. That's when I started, Megan, knowing more than the doctors.
Doesn't that irreversibly inhibit COX enzymes in your liver
Yeah,
and your stomach?
causes problems.
We're here for a good time, not a long time.
Who supports what you got? Most people should die when they're 35 anyway.
Yeah, for sure.
If you don't brush your teeth will fall out when you're 35. And when most animals' teeth fall out, that's when they die. So humans shouldn't live really much past 35.
Everything else is brought to you by science and technology.
Yeah, and mostly your dentist.
And dental work.
Yeah, dental work.
Are dentists okay, or they should also do research somewhere?
Dentists are okay. I mean, I feel like they provide a valuable service that I can't.
You can't clean your own
I can't
teeth
clean
with
my
the
own
little
teeth.
thingies.
No. My dentist actually uses a sandblaster.
What?
It's a baking soda. It's like a baking soda spray. They don't polish my teeth, they spray them. With this, right?
It's gross.
I actually like it better.
It's so gross. I hated it.
I like it better. I go to, it's over on Hal Greer, Woodruff and Gonzalez.
Oh, I live in Wheeling.
Oh.
But they use that there, and
Oh,
I
okay.
hate it. I refuse.
The polishing really makes me nauseous, actually.
Mm.
The toothpaste that they use, and it gets up in my nose because of the problems. So I don't mind the sandblast. I've got a dental appointment in 2 weeks. Just think about it.
And me.
Yeah. Right on Valentine's Day, I'm going to have some shiny teeth for that night.
Putting on the Ritz.
Mine's at 9, my wife's is at 8:30. Right on the same day. It's sort of an odd.
Instead of a couples massage, you got a couples cleaning. Are they going to give you a discount? Maybe get like a 2-for-1?
I don't think so. The bad thing is I'm going to have to wait on her, or she's going to have to wait on me, right? Because I'm going to have to go half an hour early, right? Because it's not, and then she may or may not wait, I don't know. All right, pharmacodynamics, just movement of drugs, receptors. Okay, so receptors are kind of important. We're going to talk about receptors a lot in this class, and so it's really important to understand what a receptor is. Most of you know what that is. For those of you that don't know, basically you've got brain cells, right? And on the surface of those brain cells are these proteins that are shaped in a certain way that drugs or neurotransmitters can attach to that and cause those receptors to open ion channels. And they can affect whether or not your brain cells are active or inactive. That's really it. It's pretty straightforward. Now, what is important about this and what can be very, very complicated is the structure of those receptors, making sure that they are shaped correctly, making sure that they operate those ion channels on the right time scales, okay? And that's stuff that can be very, very tricky, but we don't need to really, bog ourselves down too much on that. A ligand, that's a fancy word for just stuff, right? A ligand is just a molecule, it's a substance, it's anything that's going to bind to a receptor, okay? So you will hear some people say ligand-gated receptors. All that means is it's a receptor that opens when a molecule fits in its hole and it opens an ion. That's all there is to it. Sounds really fancy. You can tell people you know all about ligand-gated receptors, and they're going to think, wow, this guy's a real genius. But really, all you know about is how a lock opens, a lock and a key. It's as I said in my other class, it's kind of a hack sort of analogy, but it's an effective one, right? And it really works. If you have a receptor for dopamine, guess what will open that? Dopamine. Guess what won't? Serotonin, right? Other things that are shaped a lot like dopamine, that will open it though, okay? And this is why drugs work. So guess what you don't make inside your body? You don't make cocaine. You don't make morphine, right? You don't make meth, okay? You don't make these things inside your body. What you do make inside your body are endogenous, that's a fancy word, endogenous just means inside of you. You make endogenous substances, right? So there's a fancy thing called an endocannabinoid, right? Sounds extremely fancy. All it means is it's a substance you make in your body that's very similar to cannabis. That's it, endocannabinoid, okay? There are what we call sometimes phytocannabinoids. That simply is a cannabis-like drug you got from a plant, okay? That's the way you think, right? So that's the way you think about most of the time getting that kind of drug. If you didn't have endocannabinoids and receptors for those endocannabinoids, guess what? Those phytocannabinoids would do you no good. You could smoke all the marijuana you want and you would never get any medical or recreational effect from that, right? Nothing would happen because you wouldn't have a receptor for it. But you do have a receptor that's close enough, right, for that chemical to interact with it at that receptor site. And so that ligand, though it's not the exact ligand, right, it's close enough and it'll open it. Now, sometimes you get these fancy people in lab coats and they go, hey, you know what's awesome? Morphine. You know what's more awesome? If we take that morphine and just put a little crink in it somewhere and we make Oxycontin out of that, right? And it's even better than morphine, right? Oh, it's also not addictive. I want to throw that out there.
Sure.
So that's interesting. So what they will do is biochemists, molecular biologists, these folks will put their heads together and they'll go, hey, here's the shape of this molecule that operates this receptor. What happens if we tweak this a little bit? Does that change the half-life? Does that change how effective it binds to that receptor? Does that change the toxicity levels, right? Whether or not there are side effects, or what are those side effects, right? And that's what folks have done. So there are sort of two classes of drugs that we would think about, or substances, right? We would think about endogenous substances, things you make in your body. Exogenous means from outside your body. Those are the drugs. When we get to the drugs, there's sort of two categories there even. There's the natural and the synthetic, right? And sometimes with opioids, we think about things that are semi-synthetic, but whatever, right? So a natural substance is the marijuana plant, right? So you grow the marijuana plant, you do whatever you want to do to that, and you get that into your body. There are also, they call it synthetic marijuana. That's a little bit of a misnomer. Yeah, don't mess with that stuff, because that will cause you a psychotic breakdown, big time. And the reason for that is, and hopefully it's some of you who has marijuana, who has the presentation on marijuana. Let me change that. I want to make sure that I ask the right person. Who's got marijuana? Nobody's hands are going up. I think somebody in this class should have a presentation on marijuana, right?
I think they all dropped. Is that over there?
You think they all dropped? That's going to be interesting. We'll figure that out. So hopefully will tell us this. The reason synthetic marijuana is not really an accurate sort of description in my mind is marijuana itself has many chemicals, right? THC being the primary one, but they're like cannabidiol, right? Like CBD. Yeah, CBD oils are a big thing right now, right? My sister-in-law gives that to her cat. She's got a... True story. Her vet said, you need to give it some CBD oil because it's, you know, it needs to relax a little, right? It's just this over-anxious cat. The point of this is, if you use marijuana, it has THC and it has primarily CBD is the other kind of important guy, which really sort of gives you a protection against those, you know, psychotic episodes. If you have synthetic marijuana, it's really just synthetic THC, and it doesn't have those other chemicals, including CBD. And so you're yes getting the THC effects, but you're not getting that protection, right, Brandon? So you're not getting that sort of thing, and so you end up just running down the street to the police station because you don't know what's going on, right? It happens. Who was the football player that did that? Like he did some K2 or something, and I mean it was legal wherever he was, and then he just took off running to the police station because he was having some weird effect. So there's like this, like, you know, giant football player like running down the street to the police station because he was having a psychotic episode. But you do have to watch those. Generally, you know, I say natural's better, right? Because you're getting kind of the, at least with marijuana, you're getting the full suite of those substances, right? All right. Hey, there you go. There's a receptor. There's a drug or neurotransmitter. What's the fancy word for that? That fancy word is ligand, right? It's going to bind to that receptor, and it can do different things. It can open an ion channel, or it can have some other effect, and often it'll have some other effect. We can talk about those as we need to. Okay, you don't need to know anything specific right now. Just know ligand binds to a receptor, and then it starts some action that you know, creates a change in your, you know, the way your neurons work. It's that simple. I mean, here's sort of another example with steroid hormones. We won't talk as much about this, but we can, but it will affect, you know, like DNA and RNA and your protein synthesis, which is kind of interesting. Hormones. Yeah, hormones typically screw around with gene expression. Okay, we do want to think about agonists and antagonists a little bit, right? So whenever we think about drugs, whenever we think about whether that's an illicit drug or a prescribed drug, you know, for medical purposes, whatever it is, we really want to think about what is the neurotransmitter system, right? Or systems that it's altering, right? Or mimicking, right? And so what is it preventing? What is it sort of boosting, right? And that's how we want to think about things. So if we think about something that is an agonist, okay, that means it's going to boost the effect of that neurotransmitter. So if something like cocaine is a dopamine agonist, what that means is it's going to give you more dopamine or increase the effects of dopamine, okay? If something is a dopamine antagonist, right, it means it's going to shut down the effect of dopamine. And we can do this, I mean, we can do this in a couple handfuls of ways, right? I mean, there are really a number of ways where we can get in and we can affect the, you know, that process. We can provide you with precursor elements. So if you think about, how many of you guys know about Parkinson's disease? Yeah, one of the #1 treatments for Parkinson's disease is called L-DOPA, right? L-DOPA is a precursor to dopamine. So basically we're giving you need to build a house, we're giving you lumber, right? You take that lumber, you build a house, okay? So it's a precursor, it's an agonist, okay? There are other ways that you can have dopamine agonists, right? There are things called monoamine oxidase inhibitors. Monoamine oxidase is an enzyme that breaks down dopamine, okay? If we inhibit monoamine oxidase, guess what? We have more dopamine available, right? Okay, so it's kind of a fun situation there. So that's kind of different ways that we can do an agonist. We could help storage of that neurotransmitter so we can release more of it later. We could actually release the synaptic vesicles, you know, those little bubbles that are holding onto the neurotransmitter. The other thing that we can do is we could actually mimic that neurotransmitter directly and bind to the receptor and open that channel. So that's something we can do as well, right? Basically, the exact opposite is going to happen if it's an antagonist, right? We can block a receptor but not open the channel. That's pretty cool. We can destroy synaptic vesicles, so we're not able to store up the neurotransmitter. We could eliminate some of the precursors, right? So if we were breaking down some of that, we could enhance those enzymes, right? So instead of inhibiting monoamine oxidase, if we wanted to enhance the activity of monoamine oxidase, then that would be a dopamine antagonist. It's really pretty simple. You just want to think about what's the neurotransmitter, are we increasing or are we decreasing the effects of that neurotransmitter? Don't worry too much about it. They're giving you like direct agonist and antagonist stuff there. There are some things with like partial agonist and partial antagonist. That's actually kind of an important story we should think about, right? And a great example of this is actually Parkinson's disease. So the number one problem with someone who has Parkinson's disease, they're losing cells that release dopamine. And they're losing them in a particular brain region that's not terribly important to you, but it's a small place, going from the substantia nigra onto the striatum. So what we're going to do is we're going to give them more dopamine, right? We give them that L-DOPA, they can make more dopamine. That's awesome. The problem is once you make too much dopamine, you start to develop schizophrenic-like symptoms, right? And so if someone has schizophrenia, one of the first things we do is we give them a dopamine antagonist so we can reduce the amount of dopamine. Of course, the problem with that is once we've reduced your dopamine levels too far, well, then you develop a movement disorder, right? So I know, so do you want to hear voices or do you want to be able to move, you know? And that's kind of the choices. And whatever decision, you know, wherever you are, you try to move to the middle, but often you overshoot, right? So what they have now are partial agonists and partial antagonists, right? They work better than nothing, but not as great as, you know, full-on dopamine, right? And so you could boost levels a little bit everywhere, but not so much you have a problem, enough to alleviate some symptoms, but not so much to create some of those side effects either way, the agonist or the antagonist, right?
Isn't the, is it tardive dyskinesia, is that what it was?
Yeah, tardive
Isn't
dyskinesia.
it like permanent once
It
you
is.
get it?
Yeah. Once you develop a movement disorder because you've been taking a dopamine antagonist, that's gonna, you've got that for the rest of your life. So, yeah. So you really have to watch. That's why these partial guys are such an improvement. And I think, as I was telling someone earlier today, the next step, and this is not something you need to know now, are these things called bespoke receptors, where they're going to make a receptor, or they're going to make a special receptor, squirt that DNA into your brain cells, and then give you a pill that'll activate that receptor. But it's going to be a substance you don't normally make in your body, right? So if we were to give you a pill now with a ligand in it, and you don't have a receptor for that, nothing happens. It comes out, right? You take it, you excrete it. If you have a special receptor for that, though, then you can activate that receptor because you've got a receptor for it, same as you have any other receptor. I think there's a lot. That's only been around, 2 or 3 years, but that's going to.
I think it's really cool.
I think it's super cool, and I think in particular for something like Parkinson's disease, it is the solution. Because we have not, unfortunately with stem cell research, been able to replicate dopaminergic cells, and even if we could, there's no guarantee we could put them in there in the right way, because you've got to fit those in there somewhere. But I think the bespoke receptors, but you don't have to worry about that too much. If you get really excited about it, that's great, they're cool. We talked about antagonist. We do want to say if that ligand binds to a receptor, it is temporary. It doesn't happen forever. It binds for a little bit, and then it's released, okay? So you want to keep that in mind. We can bind to that receptor again, maybe with another molecule, maybe with the same molecule, right? But it's not a permanent, right? Now, how long that lasts, how readily that happens, that's all going to be based on the structure of that ligand and the structure of the receptor, right? The more readily they bind and the stronger they stay bound and the longer, we call that affinity, right? That's the higher the affinity that they have, okay? So if something has really high affinity, it's going to bind and it's going to get stuck there. It's going to be awesome. If something has low affinity, then it's like, well, I guess she's all right. So Some of you may have been in relationships that were high affinity, some may have been low affinity relationships, right? Like, well, this is going to work for now, for the next 2 weeks, this is pretty awesome, but I don't know what's going to happen beyond that. And then sometimes you get in a relationship and you're like, oh man, been in this thing 6 years and I don't know how to get out. Somebody's been in one of those. Somebody's gonna own up to it. Upregulation and downregulation, this is pretty simple. Basically, you're either going to increase the number of receptors or decrease the number of receptors, right? Often you will do this, you'll do downregulation typically, in response to chronic use of a particular drug, right? So this is part of that tolerance mechanism. Once you've been taking a drug for a long time, your body wants to be at that sort of homeostatic level, right? Whatever that is. And over time, what you'll do is you'll stop inserting as many receptors into the membrane. So what you need is more drug to activate just those few receptors that are present, right? That's why you have to take more and more and more drug. Now that's fine, okay? Once you stop using the drug, you kind of have that reverse process, right? Where you're eventually going to get back to where you're putting in that normal amount of receptors again, so that's fine. The real problem with this is folks, you'll often see folks who've been clean for a long time, and then they will have a slip up that's perfectly normal, but they will actually overdose on that slip up. And the reason for that is they didn't accommodate for the fact that they had developed tolerance. They had been using heroin for 6 years, and they developed a pretty substantial tolerance to that. They've been clean for 2, they had a slip up, and they went back to that same dose of heroin they were using at the end of that 6-year period instead of that initial dose of heroin, right? And so I think that's an important thing to get across to people. If you or someone you know has been dealing with addiction or drug abuse, and somebody gets clean, just be prepared for a slip up. We're people, and we can talk about those mechanisms later. It's going to happen. Don't be surprised by that. Don't be discouraged by that. It's just going to happen, and you should prepare for it, right? I take a little bit of a different approach on that than some other people. Some people are like, oh no, you're going to be clean forever. No, you're not. Be clean for a couple years maybe. Let's just be prepared to get you through the next time that you're not clean, right? And so I think we need to really make sure you're safe and set for that. And just keep in mind, drop the dose back down, right? Go back to that low dose, and hopefully you can get through that without an overdose and death situation. Because it's going to happen. It's going to happen. Even those of you who have tried to quit things that were not, how many of you have ever tried to quit biting your fingernails? Yeah, right? And what happens? Once in a while you'll bite your fingernails, right? Yeah, it happens, right? It's not a problem. But it's just the mechanism. We can talk about receptor subtypes now. Basically, there are variants of receptors, and they have different characteristics, right? And they're in different places. A good example of this are the opioid receptors. There are 2 or 3 different kinds of opioid receptors we'll talk about later. Each one sort of mediates a different effect of the opioid itself, right? Which is kind of cool. And so that's a lot of work. Once we understand receptor subtypes, there's been a lot of work in developing drugs that only activate certain subtypes. Because if they can just activate the part that alleviates pain, but not the one that develops dependence, well then maybe we actually might have an opioid that's not addictive. So, and there's some folks working on that, which is pretty exciting. And not in the same way, so the biochemists have said it's not addictive, not the marketing.
Gotcha.
Not the marketing team. If the marketing team says it's not addictive, that's different. If the scientist says, hey, we jammed it down the throat of these rats and they never got addicted to it, that's a whole different story. Don't worry about this too much. I mean, these are just different kinds of drugs. I'm not going to ask you too much about drug shape and structure. Do keep in mind that there are differences in drugs. If they're all in the same class, they'll have some similar characteristics, right? And my guess is, to most of you, all 3 of these probably look the same. And if I said, hey, find the difference, you're actually going to be searching for a little bit to figure out what the difference is. If you're used to looking at drug structures, or in these drugs in particular, you're going to go, oh, well, we've got different things going on in these different locations, and some of these bonds are going to be different and so forth. I don't want you to spend too much time on that. Just know these small differences, what you think is a small difference biochemically can make a huge difference in the effect of the drug and what it does to your body. Okay? You know, just hanging a hydrogen somewhere can totally change the world. So there you go. Dose response curves, those are important. Basically, we're going to give you a drug. How much of it are we giving you versus what kind of response are you getting? Often there's something called ED50 and ED100, right? So like ED100 is like the maximum response that you're going to get. Like you give that drug to everybody and everybody's going to be like, oh yeah, I feel better. There's always a plateau, right? So how many of you have ever ingested a lot of caffeine? I'm assuming most of you have, right? Some of you, if you've been to Starbucks, they've got a needle waiting on you when you go in. They just stab you with like 300 milligrams of caffeine. Brandon, if you know anybody who's taken any sort of like pre-workout supplements, those things are jacked up with 300 and 400 milligrams of caffeine, right? It's a lot of caffeine sometimes. You really got to be careful. But there's a plateau, right? I mean, you take caffeine, what happens? Your heart rate increases, okay? Your heart rate's only going to go so fast, right? Doesn't matter how much more caffeine you take, your heart rate's not going to get any faster, right? It's going to cap out somewhere. So there's always a plateau, right? Now that plateau can be at a different place, right? So sort of that CNS stimulation you get from caffeine, let's say that's going to cap out here. The CNS stimulation that you get from methamphetamine, still going to get a plateau. That plateau might be up here, right? It's going to be at a different place, okay? But you are always going to hit a plateau. Even if you take more of the drug, you're not going to get necessarily a bigger effect. Side effects can get bigger, and you always have to worry about running into that side effect called death, right? So that's one. Morphine's like that. There's a certain point where you take more and more morphine, it's not going to help you feel better, but it will definitely prevent you from breathing, right? So you got to watch out for that. So that's how we think about potency, right? So here you go. Here's an example. These are all pain relievers. Okay. Again, how big of a dose do you need to get sort of that maximum effect? Here's aspirin. You got to take a lot of this to get just a little bit of an effect. You don't have to take much morphine or derivatives of morphine at all, right? I mean here we're talking about 1 milligram, right? 1 milligram of this drug and like 75% elevation in your pain threshold, right? That's pretty massive. So that's a pretty effective drug. The problem is you worry about the side effects of that, right? What are those side effects? It's not to say there aren't side effects of aspirin or codeine. There are, right? They're just typically not as immediate or as profound as with some other drugs. You can calculate, if you want, therapeutic index, right? Toxic dose and effective dose. There are different things that folks will take into consideration for this. Sometimes you'll see something that's LD50, that's lethal dose 50, right? We're just kind of thinking about the same thing here. Now, in practice, we're not necessarily, so this sounds a little, now you're a little worried, right? It's like you go to the doctor and they say, well, here's a drug and you know it kills about half the people that take this dose, but here you go, you got a 50-50 shot of making it. Or at the effective dose, nobody wants to take a drug that's got a 50% chance of actually helping, right? So that doesn't make any sense. Like, well, you know. So often what they will do is they will have like 99 and 1, right? So you'll have like an effective dose for 99% of the population, and here's the toxic dose for 1% of the population. And you'll try to find a dose in the middle there that works for people. So that seems more reasonable, right? If you went to your doctor and they said, this drug has a 99% chance of working, you're going to be more likely to go, okay, 99% chance of working, 1% chance of killing me. That's better than 50-50. You know. All right, there's just, giving you some idea about, we don't have to think about this. Competitive antagonists, we sort of talked about this a little bit. But this is why things like naloxone will work, right? Because it's a competitive, it will actually, it'll actually bind in the same place. In this example, they're mentioning morphine, but whatever. opioid you want to plug in there. It'll compete with that opioid for the same binding sites, but it's not going to produce the effect, right? This is why some of these competitive antagonists can be used as rescue drugs for folks who have overdosed, right? Because they'll get in fast, they'll compete for those same binding sites, but they're not going to have any effect. They're just going to sit in there and prevent the opioid from doing anything, right? And so that's why these particular drugs work, or how they work, I should say. Don't worry about that too much. Non-competitive is a little different, but we're dealing with a similar situation. Non-competitives are, they don't bind to the same binding site, they'll bind to a different binding site and shut down that process from somewhere else. So that's all that means. Competitive, it's going for the same binding site. Non-competitive, it's going for a different binding site. Okay?
I think the same thing as allosteric regulation.
Let's see if we can get something. That's a good question. You said allosteric inhibition, right? Mm-hmm. Always trust Wikipedia. I was hoping there was a diagram. I'm just going to show it to you. But yeah, it's basically the same idea. But I had assumed that there was a better picture than that. Sorry. That's not a good one, and you're not going to get anything out of that. But yeah, it's basically the same idea. You're not going for that binding site. You're going for something else, right? Which has some advantages, obviously, right? You don't have to wait on that ligand, whatever it is, to dislodge. In this case, you don't have to, compete with it for that binding site. You can just bind somewhere else, provided that binding site's open. Get in there and do your business. Hey, here's a shocker. Some drugs interact and reduce the effectiveness of each other. That's not a surprise for her, right? I mean, sorry, Katie. I know this is like a real big reveal right there for you, right? You weren't ready for that. Also, glad you're sitting down. Some drugs have additive effects. I know, right? Who would have ever thought you could take two drugs and get a bonus out of that? Sometimes these will work synergistically, right? And so what you will get is actually when you take these two drugs, you'll get a greater effect than either of those drugs independently, right? So sometimes when you take two drugs, instead of getting just A plus B, you get A plus B and something else. You get that little bonus, okay? Here's the example of additive effects. I mean, it's just potentiation. Talked about tolerance. Okay, we've talked about that some. Cross tolerance is kind of interesting. This is when you take. Oh, sorry, Seth, you had a question?
Yeah,
Isn't it like a buzzer?
Isn't a lot of times like the additive effect dying?
Well, it depends. But yeah, no, you can definitely. That's the real concern with this, right? Is that you don't want to do too much, right? And often these drugs that interact, you can't. A great example is serotonin syndrome. We'll talk a lot about serotonin syndrome later, right? This was one of my, I don't know, I was at the Healthy Life Market there in Barboursville by the mall. I don't know if you've ever been there. They have a decent beer selection sometimes. And so there was a guy who works there, and somebody had called in, and they were asking about St. John's wort. I don't know if anybody's ever used St. John's wort, right? That's fine. You can do whatever you want. And they were asking him about it, and he said, I don't really think you should take St. John's wort with your SSRI. But he said, I'm just a guy who works at a health food store. You should talk to your doctor. And I thought, well, that gives me some confidence about that guy. Right? But the problem there is St. John's wort is a it's a serotonin agonist, right? And SSRIs are serotonin agonists. And so you get those additive effects, cause some problems. Serotonin syndrome. We'll talk about that later. So no worries about that. But yeah, absolutely. You think additive effects are typically positive, right? Yeah, but sometimes they can be negative. All right, so cross tolerance. I don't think I finished that. Basically, what we mean here is you take a drug, and then some other drug that's similar to that doesn't work as well in the future, right? So if you were to take one opioid for an extended period of time and you develop tolerance to that, if you were to take a different opioid, it might not work as well, right? Because some of the same mechanisms of tolerance are going to be still at play, even though you're taking a different drug, right?
Would
If
that be like taking heroin as opposed to like some other kind of like painkiller or something like that?
Yeah, absolutely. Now, if you switched over to cocaine, no worries there, right? No tolerance to cocaine because it's a completely different class of drugs.
Right.
Okay. But anything that's going to be similar, that's going to use similar receptors or the same receptors, same enzymes, right? You're going to see some cross tolerance. Something to think about. You guys have a pretty good idea about tolerance. Metabolic tolerance, we're thinking about liver enzymes and so forth there. Pharmacodynamic, we're thinking about down and up regulation of receptors. We talked about that, not a big deal. Skip through a lot of this. You guys wanted to see you didn't want to skip through that?
No, I'm just trying
No, I'm
to
just
keep
trying
up
to,
with you.
yeah, I'm trying to keep up with you.
So,
Yes, absolutely.
Absolutely, thank you.
100%.
anytime.
Oh, look at the little spoon it's got. Oh my God, a little spoon and a razor blade.
It looks like a
Hell.
baby. It looks like a baby spoon. It looks like a baby
Because it has
spoon.
like that guard on the end, yeah.
It does, doesn't it? That's what I thought. I was like, I don't know much about baby spoons, but that definitely looks like a baby spoon.
That's terrible.
It is terrible.
Sorry about that, guys.
But I guess maybe you can get the right bend on the, I don't know. Now I'm thinking about it. But now I'm thinking like with that guard on there, the handle's not gonna bend much, right?
Well, like sometimes they're also like, I don't know.
But now they make them all out of like plastic,
Yeah, it's
right?
like
That's not gonna be any good.
no.
Don't, that's not gonna be any good. That's gonna melt.
Yeah.
Maybe they should make all spoons out of plastic for drug
No,
use.
I had a dishwasher incident
Yeah.
at home. Don't talk about it.
There was a spoon and a needle outside of Domino's the other night.
Really?
Oh, that's good. I found a needle in my yard before. It's like,
Yeah.
oh, well, keep it classy, Huntington.
It happens, folks. This is why we need more support for folks who are dealing with these issues.
We need a drug exchange program. Or
yeah.
a needle exchange program.
We have one. I
Yeah,
mean,
it's at the health department.
yeah.
Is it an exchange?
It's
or
not an exchange.
It's not an exchange.
Yeah.
You can.
But it's not
They don't make you.
required.
Yeah, we need an actual exchange program.
Yeah, I mean, I understand. I mean, it's tough.
Yeah,
It's tough.
it's a fine line.
It is. It is. Probably what would be nice is, they have, John, was it your group that told us about the Vancouver project?
I don't think it was.
You don't think it was you?
No, I can't remember what group it was actually.
But you remember that?
Yes, I remember it.
So in Canada, they have some cool places where if you are a drug addict, you can go, and they have like medical professionals there.
It's like safe injections, like it's
Yeah.
supervised injection.
Yeah, which is pretty. I mean, so I kind of live by the rule: if people are going to do something, I should make it as safe as possible for them, and then secondarily, if I can make some money off of it, I should do that. So that's a separate process. I don't know if there's a lot of money to be made in this situation, but they have these safe injection sites where folks can come in and they can. One, it keeps all of the paraphernalia sort of contained. It prevents the spread of, one of the big problems is, hepatitis, HIV. A lot of these diseases can be spread through the use of these drug needles, use needles and so forth. So it kind of prevents that. It also prevents any overdose issues. I think that program's been running for a number of years now, and I think it's going to take me a while to count up their number of overdoses because it's 0. So it's a very effective program for that. So I think I don't know. So there you go. Something like that would actually make a huge impact.
Yeah.
Because then you don't have to, and folks can come in and it's not, now they don't provide the drugs for you, but if you come in with your drugs, they'll provide everything else you need.
BYOD.
Yeah, yeah, absolutely. Because they're not going to give you
Right.
any illegal substance, but if you walk in with it and there's no risk of, like police intervention or anything. You walk in, you do your business, and you leave. And there's not like any ID process or anything. I don't think there's an ID process. It's pretty cool. Yeah, I think it's called the Vancouver Project, right, or something like that. It's in Vancouver, is where they started, but they have a few sites across Canada now. Not a big deal. Hypothermia, we don't have to think about that. Conditioning, state-dependent learning, you guys know about this stuff.
Right. Gotcha. Got it.
Sensitization. Don't worry about that too much. Pharmacogenetics, we've talked about that as well with the P450 business. These polymorphisms. Again, we've already said they don't do screening. I'm at the end now.
Really? You don't say.